Hi dear student, welcome to my channel Education Shop. In this we will solve example 3.6 that is taken from the book Heat and Mass Transfer by Singhal. This example 3.6 is relevant about heat loss to a composite valve. The composite valve section is given in the diagram also. Let's come toward its statement. A 3 meter high and 5 meter wide valve. The dimension of the valve is given. Let me write it first. Height of the valve 3 meter, width of the valve that is 5 meter, cross section area of the valve is simply just multiply this 5 with 3 and you will get 15 meter square. Consists of a long 16 centimeter 22 centimeter cross sections horizontal breaks. This valve consists of 16 by 22 centimeter horizontal breaks. This is the break that you can also see from the diagram. Its height is 22 centimeter and its thickness is 16 centimeter. Thickness of the break, that is LB, let's say, and it is 16 centimeter divided with 100 to convert into meter, and it is equal to 0.16 meter. And the height of this break is 22 centimeter, means to say that is divided with 100 to convert into meter, that is 0.22 meter. The height of the break, that is 0.22 meter. Thermal conductivities of the break is 0.72 watt per meter Kelvin. Separated by 3 centimeter thick plaster layers, and its thermal conductivity is 0.22 watt per meter Kelvin. Means to say the two breaks, this is first break, this is the second break, and in between these two breaks the plaster is in between, that is separated by distance of 3 centimeters. And it is 0.22 watt per meter Kelvin. There are also 2 centimeter thick plaster layers on each side of the break. This is the side of the break, and there is also plaster layers and its thickness is 2 centimeters. On the other side of the break there is also plaster layers there and its thickness is also 2 centimeters. Now the thickness of the plaster, that is 2 centimeters, you can see it means that is 0.02 meter. And also it's a 3 centimeter thick rigid form. This is the form. It is talking about this form that is of 3 centimeter thick. Let me write the thickness, that is, let's say LF for the form. Its thickness is 3 centimeter, means to say 0.03 meter, and its thermal conductivity for the form is also given. The form is given on the inner side of the valve. As you can see, this is the inner side of the valve and this is the outer side of the valve. At the inner side you can see there is a foam provided on the plasters, but in outer side there is no foam provided on the plaster. In order to reduce the heat transfers, that's why we provide this foam. The temperatures on the inner side is 20 centigrade. This is, let's say, 10.1, that is 20 centigrade, and the temperature at the out is minus 10 centigrade. And also the convection heat transfer coefficients. The inner side and outer side is H1 and H2. H1 is 10 watt per meter square Kelvin and H2 is 25 watt per meter square Kelvin. And what we need to find the heat loss to this composite valve. That is our requirement. Let's come to its solution now. As you see from the statement, valve height is 3 meters and its width is 5 meters. So this is not the complete valve that is given in the diagram. It just given some portion of the valve that is under our study. We will find heat transfer through this portion of the valve that is under study. Then we will multiply with the area ratio to find the total heat transfer through the valve. So let's consider the sections of the valve that is under our study. First of all, the height of the section is simply add 1.5 to 1.5 centimeters. It will give you the height of the section. This is, let's say, and that is 25 centimeter divided with 100 to convert into meters, and it will be equal to 0.25 meter. For the sake of simplicity, calculations take the width of this section is 1 meter. Then it means that the cross section area of this section is simply 0.25 multiplied with 1 meter, and it will give you 0.5 meter square. Inner side and outer side, the heat is first transferred to this foam surface by convection heat transfers, and then from this surface of the valve to the at some distance outer side, again convection heat transfer. So the resistance that is offered to the inner side of the convection heat transfer is this is, let's say, Ri, and the resistance that is offered to the heat transfer at the outer side of this valve, that is, let's say, R. not. This form also offers some resistance to the heat transfer. This is, let's say, R1. Now let me write the thermal resistance network diagram for it. The temperature is T infinity 1, and resistance to the convection heat transfers at the inner side, that is I. And next is the resistance that is offered by this form. This is, let's say, R1. Then and the next resistance that is offered to the heat transfer is this plaster, is R2. If you see when heat is transferred through these sections, that is under our study, whose height is from this point to this point, from this line, from this top line to this bottom line, this section of the valve and this section of the valve, when heat is transferred through this section that is breaks, and then again this sections, first plaster and breaks and plaster again. So when the heat is transferred through this, some heat transfer pass to this way, some heat transfer is passed to this way. What will happen? It will offer the resistance to the heat transfer in parallel, as these layers are parallel to the heat transfer. That is, let's say R3, this is, let's say, R4, this is R5. So the resistance that is offered by this faster portion, this break and this faster portion are in parallel, the heat transfer, and it is denoted by R3, R4 and R5. So I can say that this is R3, R4, R5, and then finally the heat is transferred to this section of the valve, that is again plaster, and it offers resistance, let's say R6, and then heat is transferred from the surface of the valve up to some distance outside, it is R0. And finally the temperature dropped to T infinity, it is minus 10 centigrade, and this is 20 centigrade. Let me write on this diagram that what kind of resistance is offered by which sections to the heat transfer. First resistance, that is R1, then R2, R3, R4 by the breaks, then R5, this portion of the plaster, and R6, this portion of the plaster, and then R0. The first resistance need to calculate is R, that is equal to 1 divided by H1A. This is the resistance that is over to the convection heat transfer. That's why it is 1 over HA. 1 divided by, what is the H1 value? That is 10 multiplied with area. The section that is over under study is 0.25. After solving this, you will get its value, that is 0.4 centigrade per watt. Next is to find the resistance R1. This form resistance, that is mode of heat transfer through the form is conduction heat transfer. We can say that it is LF divided by KF and its area. LF is the thickness of the form, it is 3 centimeters, means to say 0.03 meter, divided by thermal conductivity of the form, that is 0.026, multiply area of this form, that is simply multiply 1 with 0.25. Here you can see that is 0.25, and that is equal to, after solving this, you will get its value, that is 4.62 centigrade per watt. Resistance R2 and R6 are same in dimension, same in natures, have same thermal conductivity, so the resistance for R2 and R6 must be the same. We can say that R2 is equal to R6, and that is equal to L divided by Ka. What are its thickness? The thickness of this plaster layer is 2 centimeters, divided with 100 to convert into meters, that is 0.0, and the thermal conductivity for the plaster is given, that is 0.22 watt per meter Kelvin, and the thermal conductivity for the break is Kb for the break, that is 0.72 watt per meter Kelvin. That is 0.22 multiplied with the area. Simply multiply the height with 1, you will get its area. Its height, that is 0.25 meter. When you solve this on calculators, you will get its value for the resistance R2 and R6, that is 0.36 centigrade per watt. Next is to find the resistance R3 and R5. This is also same in the dimension. This is R3, and similarly this is R5. It have same dimension, same thermal conductivity. That's why we can say that R3 and R5 must be same, and we say that R3 is equal to R, and that is L divided by K. What is its thickness? That is, if you see that its thickness is 16 centimeter, thickness of R5 and R3 plaster. 16 centimeter divided with 100 to convert into meters, 16 by thermal conductivity of the plaster is 0.22, that is given in the statements. Here you can see that, and the area, and its area is very simple. Height of this segments of the wall is 1.5 centimeter, mean to say 0.015 meter, and we assume that width of each segment is 1 meter. So when you multiply this h with 1 meter width, you will get area for this section 3 and 4, that is 0.015 meter square. That is 0.015. Simply solve this on calculators. You will get the R3 and R5 value, 48.48 centigrade per watt. Next is to find the resistance offered by this brake to the heat transfer. It is, let's say, R4, and is L divided by Ka. Thickness of the brake. The thickness of the brake is 16 centimeter. Convert into meter. Just divide with 100. Get 0.16 meter. So in the previous calculation, we have written 0.016. That is not 0.016, but it is 0.16. Because when you convert centimeter in meter, you will divide it with 100, and you will get 0.16 meter. And then divide it with these values, you will get the R3 and R5 value. That is 48.48 centigrade per watt. Similarly, the thickness of the brake is 0.16 meter, and its thermal conductivity of the brake is 0.72 watt per meter Kelvin. The area of the brake is very easy. First convert this 22 centimeters. The height of this brake is 22 centimeter. Convert into meters, divide with 100, and you will get 0.22 meter, and multiply with the width. We have assumed up to 1 meters because we are solving all the segments of the wall up to 1 meter width. That's why we multiply with 1 meter width, and you will get the area of the brake. That is, let's say, AB, and that is 0.22 meter square. Just right over here, that is 0.22. When you solve this on calculators, you will get resistance that is offered to the heat transfer by the brake, that is 1.01 centigrade per watt. Next is to find the final resistance that is offered to the heat transfer, that is R0 outside of the wall. Is 1 divided by H2. It is 1 divided by H2. H2 is 25 given in the statement, and the area of the section, that is 0.25 meter square. So on calculators, you will get the R0 value, that is 0.16 centigrade per watt. It means circle all the resistance value that I have calculated. Don't get confused with it. This is Ri value, R1 value, R2 and R6, R3 and R4 value, R0 value. If you see the thermal resistance network diagram, the resistance R3, R4 and R5 are in parallel. So we will find its equivalent resistance, that is, let's say, Rm, and then you simply add all the resistance and you will get the total resistance. So the resistance that are in parallel, first we will solve that. So its equivalent resistance, let's say, Rm, that is equal to 1 over R3 plus 1 over R4 plus 1 over R5. Now put the values. 1 over R, what is R3 value? R3 value is 48.48, and it is also equal to R5. The resistance offered by the brake, that is R4, at 1.01 centigrade. Again R5, that is same as R3. I am finding this Rm value. Let me use calculator, find its Rm value. If you open the calculator, this button, we are interested to find the Rm value. Instead of Rm, you will write X on the display again, and press this calc buttons. You will see a symbol on the display. Now enter the values of R3 value. Now simply enter the value of R3, that is 48.48. Now you have written these equations for Rm. Now press this shift button, calc, solve for X, yes, and it will give you the value of X, that is 0.9696, and this X is basically our Rm value. So I can say that equivalent resistance of R3, R4 and R5 is equal to 0.97 centigrade per watt. And this way our thermal resistance network diagram becomes simpler. Here the temperature is T infinity 2, here the temperature is T infinity 1, here the resistance is Ri, here the resistance is R0, here the resistance is R1, here the resistance is R2, here the resistance is Rm, here the resistance is R6. So for this resistance R3, R4 and R5, we have written Rm instead of it. If you look at this thermal resistance network diagram, it's quite simple. Just simply add it Because all the resistance are in series, and in series what you do, you just simply add it. The R total resistance is equal to Ri plus R1 plus R2 plus Rm plus R6 R0. What is Ri value? 0.4 plus 4.62. R2 value is 0.36. Rm value is 0.97. R6 value is 0.36. R0 value 0.16. And simply solve this on calculator. It's a simple RT value. The total resistance that is offered to the heat transfer is 6.87 centigrade per watt. Now the heat transfer rate from the section is equal to change in temperature difference divided by total resistance that is offered between this change in temperatures. This T infinity 1 minus T infinity divided total resistance. It is inside temperatures. Inside temperature is 20 centigrade minus into outside temperature minus 10 by total resistance, that is 6.87 become 30. This minus minus become plus, and it is 6.87. Let's simply solve this on calculator. It will give the heat loss through the section, and that is 4.37 watt. We are interested to find the heat transfer rate through the wall, that is Q dot, and it is equal to Q dot S, the heat loss through the section, multiplied by the area ratio. And what is the area ratio? Area ratio is the total area of the wall divided by area of the section. Total area of the wall is calculated previously, that is 15 meters square, that is 15, and area of the section that is under our study. So we can say 0.25 by 1, and solve this calculators, it will give you the area ratio 60. Now just simply the values in this equation. Q dot S is 4.37, the area ratio, that is 60, multiply with each other, and it will give you the heat loss through this composite wall, that is 262.2 watt. This is the heat loss that is offered through this composite wall. Heat loss means that loss in terms of energy and money.